So, last class we were discussing about this protein folding mechanism and kinetics mechanisms we had discussed briefly before, and right now we are going to discuss at length the kinetics part, and that is essentially what we were going through in the previous class. So, what we started with was three different folding mechanisms. One is the framework model. So, this is the framework model, right. This is the framework model. So, you can see you start from an unfolded protein, right, then you have these micro domains. So, this is a micro domain. So, these micro domains are essentially relatively well formed like helices, and then they pack together to give you the native state, right. So, then this one is an intermediate. Okay. So, the middle one is possibly an intermediate for you, right. Now, when you go for the nucleation condensation, well, before going to the nucleation condensation, go to the extreme right, which is the hydrophobic collapse model. Now, in the hydrophobic collapse, you see initially you have a very fast collapse, where you have the clustering of the hydrophobic residues, right. So, if you consider this to be an intermediate I, and then what will happen is everything else starts to form, and here we said once you have the hydrophobic collapse occurring, it is the tertiary interactions which define your formation of the secondary structural element. Okay. So, that was for the hydrophobic collapse. So, this also goes to an intermediate, right. Now, what about the nucleation condensation model, the one in the middle? So, here the scenario is like this, that you start again from an unfolded state, you go to the step in between, where you might form something which is well developed, or you might form something which is not so well developed, that means loose, right, and then everything falls in place together. Okay. So, essentially you can see out here what happens is that you form this loose model, all the then the secondary structure defines the development of the tertiary structure, because the loose model has shades of secondary structure, the loose nucleation condensation the nucleus, and then everything falls in place without any formation of intermediate. But just think about it, that if there would be certain stabilizing interactions by in sense of certain interactions between amino acids which are present out there, then the middle one for the nucleation condensation model might become an intermediate, right. In that case, what would happen is that intermediate would stay, and then you would move on to the final structure. In that case, you might be having an intermediate, you might be, but here what we are talking about is a nucleation condensation where which does not go through an intermediate, that is what we are trying to focus on. So, then we talked a little bit about the nucleation mechanism, and this was this is one of the best examples of a nucleation condensation model with chymotrypsin inhibitor 2. As I said, it was worked on by the research group of Alan First in Cambridge, and it is a small protein, but still it is unique because it is shades of different secondary structural elements, right, alpha helix, beta sheet mixed, a random coil, well developed random coil, and all this. Okay. Now, this was the last topic we were actually discussing the other day, the transition state. So, can we apply transition state to protein folding? We will come to that again later, but let us first look at what a transition state really is. You know this, but for the sake of convenience and for the sake of continuity, let us look at it again. So, transition state is a structure that is at the energy maximum on any given reaction coordinate. Remember, there is not a reaction coordinate, there can be many reaction coordinates, right. A couple of bonds might break, not exactly one bond. So, in that case, then you can take one bond to be the reaction coordinate, you can take the other bond to be the reaction coordinate. So, hence reaction coordinate, it is not just one, it can be multiple, right. But for chemical or for molecules where you have only a few bonds breaking, then the reaction coordinate is essentially those few bonds, say. But for a protein, when again we said that essentially there is no covalent bond, right, it is all very loose interactions. In that case, the reaction coordinate is really multidimensional, because you can follow any trajectory, or you can follow any reaction coordinate. Okay. So, that is why it becomes very complicated. Now, how would you conventionally define a transition state? And this you know, on a 3D surface, transition state is defined as a saddle point. Now, what do you mean by saddle point? I will show you the figure in the next slide. So, saddle point means you think about a horse saddle. A horse saddle looks something like this, right. So, the horse saddle looks something like this. So, that means the saddle is kind of a pit if you are coming from this side. Okay, but if you are moving in an orthogonal direction, then it is not a pit, it is a high energy, right. So, that is what it means. So, that means you are giving along, if you are moving along a reaction coordinate where a bond is breaking, then you are going like this and you are coming down. Okay. And if you are coming from an orthogonal reaction coordinate, then what happens is it goes like this. It is like a mountain pass. A mountain pass is like this, where you can easily pass over, but then if you look at it from the down, what happens is it is a barrier for you. So, that is what essentially a saddle point is. Now, that is precisely what is being told to you in the figure. Now, look at this very carefully. So, this is what a saddle point is, right. This is a saddle point, you see where it is, this is where it is, and if you start from here and you come here, does not it look like a horse saddle? If you join these 2 points, it looks like a horse saddle, right. So, then if this is one coordinate and if you are now moving along the perpendicular direction, you think about this, you are moving, you follow the red curve, you follow this red curve. Okay. Now, you follow this red curve, you see this red curve being drawn out here. See what happens to the red curve. The red curve is now perpendicular to the one where you are looking at in the perspective of these 2 points I have drawn. So, this red curve is essentially not a minimum, right, it goes to maximum at the saddle point. Is it clear or not? You look at this red curve, you see this red curve where the arrow is again, right. So, this is essentially the red curve I am talking about. You look at this red curve, wherever it starts and wherever it ends, it actually goes to a maximum. That is the transition state for that reaction coordinate, is not it. But if you look at the same point, so if you look at the same point with the saddle point from the perspective of joining these 2 points, say this is A, this is B, and if you try to join these 2 points, this point is no longer a maximum, this point essentially is what? A minimum, but this is in a direction orthogonal to the one you were considering before. So, that is essentially what a saddle point is. Okay. So, that is how a transition state is conventionally defined as a saddle point. It is a maximum in one direction, but is a minimum in a direction which is orthogonal to it. Okay. So, this is what your transition state is in terms of a saddle point. Okay. It is called a saddle point because it looks like a horse saddle. That is why it is called a saddle point, precisely that is what it is. Okay. Now, this is what we have discussed before. In chemical reactions, only a few bonds are being made or broken in the transition state, and since these bonds are strong, one needs to apply quantum theory. Okay. So, in a chemical bond, you would be having fully developed covalent bonds. One covalent bond would snap, say, another covalent bond would form, or a couple of covalent bonds would snap, it does not matter in which order it is. Okay. And because these covalent bonds are obviously strong bonds, then you would have to apply quantum theory. Okay. Now, this is essentially what Eyring's theory is, right. Eyring's theory is dependent upon what? How a bond vibrates, because if a bond has to be broken and the bond has to be formed, before a bond breaks it has to vibrate, right. And so, that is why it is equivalent to the frequency of vibration. Okay. So, that means the rate at which a transition state decomposes into your final products should be equal to what? The frequency of a vibration times a certain energy factor, which is your exponential term. Okay. We will come to the equation again and then we will try to look at it. But when we move over to a protein, the transition state in this case is a little hard to imagine. Again, think about this. There is no covalent bond being broken. Is there any covalent bond being broken in a protein? Because your covalent bonds, essentially peptide bonds and whatever amino acids you have, nothing is changing. What is essentially changing? What is changing is your different energetics in terms of what? Maybe van der Waals, maybe hydrogen bonding, maybe salt bridges, but these are not covalent bonds per se, right. So, then if the way we defined the transition state was developed on the basis which Eyring based it on was the frequency of breaking of these bonds, essentially the vibrational frequency, then here I do not have any bonds to break. Okay. So, how do I bring this into picture? Okay. So, obviously then because these bonds are loose, then what will happen is your transition state will not be a very sharp peak. Why? Because in case of a chemical, in case of molecule in broken, your bonds are very strong and hence your transition state is very sharp. But for a protein, because the bonds are weak and because you know in a protein at any given time you can have many different conformations, then even at the transition state you can have a very diffuse transition state, that means one which is very long or very wide. Okay. So, that is what he says. For protein, however, transition state involves the making and breaking of many weak bonds that can be described by classical statistical and mechanics and Newton's equations. I do not need quantum theory for this. Now, what is the result? Hence, transition state for proteins can be very wide and long. Okay. It is not sharply peaked. So, then how do I envision it, or how do I depict a transition state for a protein? So, this is how I can think about it. So, let us consider the transition state for a protein folding reaction or for a protein folding process. Okay. Now, this drawing is exactly not to scale, but let us try to do it. So, suppose I am going from the unfolded side to the folded side. Now, let me draw it first, then I will explain it to you, then you can draw it by yourself. It is very simple actually. Okay. So, this says your free energy and this is your reaction coordinate. This is your reaction coordinate. Okay. So, because I am going from an unfolded state to a folded state, what I can say is this is u for me, this is I am saying an intermediate I, and this is my folded state F. Okay. And obviously, this is then my transition state T s. Okay. What do you see here? This is not something you have encountered before. I can tell you that. If you would be drawing a transition state, that means this energy diagram for a bond or for a molecule undergoing breakage of bonds, then what you would do is you would go from the reactant side to the product side, you would just draw a smooth curve, right, and just go over. Okay, and the transition state would be very sharp. But the problem is here, you start from an unfolded state. We know that a protein does not exist in one conformation, especially in the unfolded state. It would be having many conformations. Good. So, that means obviously unfolded state is already pretty broad to start with, right. Now, not only this, your conformations are dynamic in the sense that it is just not one set of conformations. These conformations are always interconverting among each other. So, what will happen? Because they are interconverting among each other, some conformations can be of lower energy or higher energy than the other conformations. If that is the case, what you will see is in the free energy plot you will see fluctuations, right. It will not be a smooth curve, you will see fluctuations, isn't it. So, this is what you see these fluctuations, these are your fluctuations. Okay. So, these are your fluctuations. Why are these fluctuations? Because you are considering a dynamic process where even when it is making the transition, it is still undergoing fluctuation from one conformation to the other. Okay. So, you start from the unfolded state, you come to the intermediate. Now, because it is an intermediate, before you move over to the transition state and then the folded protein. So, because in the intermediate, that means you already have progressed towards the folding of a protein, right, towards the protein getting folded. If that is so, then the intermediate should be having a less diffuse value than the unfolded state, isn't it, because now a lot of conformations are already locked, because here there is a decrease in entropy. So, in that case what will happen is the intermediate is a little less diffuse or little less shallow or little less broad than unfolded state, isn't it. Okay. Now, again you can see wiggles on this. So, even if it is making the transition, it is still undergoing random dynamic transitions between its different conformations. Now, you look at the transition state, this is what I was saying, you are breaking weak bonds, these are not covalent bonds, you are breaking weak bonds, you can be making and breaking many weak bonds, right. In that case, you will not be having a sharply defined transition state. Instead, what will you have? You will have a transition state which is very broad, right, very wide, and with again these energy fluctuations. So, this is how a transition state for a protein folding reaction, if you do consider that the transition state is applicable for a protein folding reaction, is different from that of a molecule undergoing actual scission of covalent bonds. Okay. So, in this case the transition state is wide, long, and also it has these fluctuations which are from interconversions between different conformals, right. And then obviously once you go to the transition state, and because you are applying transition state, everything else is valid, whatever assumptions you took, equilibrium has to be maintained, Boltzmann statistics, all these things are valid, and then after that it slides over to the folded state. Okay. Now, remember these small fluctuations, where have you seen these fluctuations before? You have seen these fluctuations, if you remember, when we are talking about the protein folding in an energy, in a funnel landscape. In a funnel landscape, we had many fluctuations, isn't it? So, this is essentially the same. That funnel landscape was what? It was a 3-dimensional landscape. That means, no matter what conformation you start with, you are looking at a 3D plot, each and every one comes down in a parallel sequence. Here you are reducing the dimensionality, you are trying to just present it, simplify it, but still these small fluctuations will always be there. Okay. So, this is how you would define, or you would try to model the transition state picture of a protein. Model in the sense means in terms of a picture, okay. And this is vastly different from that of a molecule undergoing bond scission. Okay. Right. Now, let us look at the model. This you know in terms of equations. Let us go into transition state theory. See, why do we care about transition state theory? Now, why do you care, where do you learn transition state theory? You do not learn transition state theory when you are doing thermodynamics. Where do you learn transition state theory? We do kinetics, right? And we have already done thermodynamics of protein folding. Now, we have to look at kinetics, and the best way for us to look at kinetics is to somehow use the transition state theory to our advantage when we are describing a protein undergoing folding or unfolding, does not matter whichever it is. Okay. Now, from the definition of I ring, what you know is your rate constant K is equal to, now this KBT, where KB is the Boltzmann constant times temperature over H e to the power minus delta G, okay, of the transition state, this is by RT. So, this is 1. Okay. Now, this is what you know, then delta G can be broken into delta H and delta S and all these things. Now, what is KBT by H? Can someone tell me what is KBT by H or KT by H? What is that? Frequency. It is frequency, and it is frequency, and it is very easy to remember. Why? It is like this, KT by H. How can you derive it? Very simply. So, remember, from a classical energy oscillator, that means E oscillator, which is classical, what is that equal to? KT, right, it is the thermal fluctuation. E oscillator classification is equal to KBT. So, this is equal to KBT. Now, you are trying to bring an equivalence. Now, what is E oscillator if you are trying to develop it from quantum theory? I can write as H nu, right. Okay. So, then if you equate these two, that means KBT is equal to H nu, or nu is equal to KBT by H, or is equal to KBT by H. Okay. So, that is why this KT by H is your frequency, vibrational frequency, right. So, this frequency is the vibration or the frequency of vibration at which the bond breaks, and hence the rate at which the transition state is breaking down is equivalent to the vibration frequency. That is essentially what it is. Okay. So, that was your I rings theory. Okay. Now, we modify it a little bit, we keep everything the same, but when we go for protein folding process, what we say is that, okay, this is what we will do. We will say that our rate constant K is equal to, nu say nu, where nu is equal to k b t over h showed before, times a certain coefficient known as a transmission coefficient kappa, okay, a certain coefficient known as a transmission coefficient kappa times e to the minus delta g dagger over r t. Let this be 2, where kappa is referred to as the transmission coefficient. So, have you heard of transmission coefficient before? So, what transmission coefficient tells you is transmission coefficient is essentially transmitting, right, transmitting in the sense that means you are starting from the unfolded state, you are going towards the folded state, and the transmission coefficient tells you that okay, if I have this many molecules on the way to the folded state, how many of those molecules actually go over to the folded state, that is essentially transmission coefficient, right, that is what it says. Now, this is again this is the equation we use for rate constant when we are talking about a protein folding reaction or a protein unfolding reaction, it does not matter which direction you are looking at it. So, now if you keep this in mind, based on this what I can write is, suppose I am looking at a protein folding, okay, that means the protein has started from the unfolded state, it is going to the folded state and it is a 2 state, there is no intermediate, okay. Now that is the assumption. If that is what we take, then I can write that for a protein folding I can write K f is equal to, right, nu, then the transmission coefficient kappa e to the power minus delta g. And if you are going from the unfolded state to the folded state, this delta g would be what? The difference between the free energy of the transition state and the free energy of what? The unfolded state. So, then I can write, so I will change this like this, what I will write is minus u by R t, where u is the unfolded state, okay, where u is the unfolded state, where u refers to the unfolded state, and this is equation 3 for us. Okay. So, then you can understand if I am going to come from the opposite direction, that means if I am, so this is what folding, if I am going to have K u, what will this delta g become? It will be this hash sign minus f, right, because now we are going from the folded side to the unfolded side. So, your starting point is the folded in case of an unfolding reaction, but this is a folding reaction. So, your starting point is what? Your unfolded state. Okay. So, just make that change. Now, we also discussed this briefly. How would you know? How would you know which part or which amino acid is involved to what extent in the actual kinetics of the protein? Okay. To put it simply, a protein has many amino acids. How would you know which one is kinetically important? How would you know which? How would you know if you are going to destroy this one, or if you are going to mutate this one, then something bad is going to happen to the protein, or something good is going to happen to the protein? That means there would be some changes in the protein. Active site, active site. Okay. Now, that is active site for what would you do for an enzyme where you have substrate catalysis and all these things. But how would you probe it? How would you probe it? How would you probe this difference? Remember, it is a 2-state reaction. The only thing I have is a folded state and unfolded state. I have nothing in between. I cannot see anything in between. So, the only way I look, the only handle I have is my transition state, because that is the only state that is probably kinetically accessible to us in terms of what the transition state theory, this equation, right. Because what is it here, k is governed by that nu times kappa times e to the minus delta g, where delta g is what? The difference between the transition state and the free energy difference in the transition state and your starting point, whether it is the folded or the unfolded state, does not matter. So, this is where it is unique in the sense that, see, if there is an intermediate, it makes it easy for us, because at least we can isolate the intermediate, we can look at it and then make some judgment, but here we do not have anything accessible to us. So, then in that case you will always have to fall back on the kinetics, which is the rate constant and hence the transition state. That means, if you are going to make a mutation, okay, and if you are going to make a mutation, say suppose you make a mutation, suppose you make a mutation, suppose a mutant is made, okay. Then suppose a mutant is made, and then what you say is the rate constant unfolding k f, and because it is a mutant I label it by a prime, okay, because now it is a mutant. So, k f prime then would be equal to nu kappa, these things are not going to change, okay, but this one is going to change possibly delta g, right, u, and this is prime over R t, and this would be equation number 4. Simple, right? I have changed the mutation, I have done a mutant, right. If there is a change in delta g, it will be getting reflected in this, and let us see where we are going from here. Okay. Now, what do we make use of these equations? Say for 3, from 3, taking natural log on both sides, we can write natural log k of f is equal to nu times kappa minus delta g u over R t. So, this would be say 5, simple, right. Then we can also, what we can also do is from 4, what we have is natural log k f prime is equal to nu kappa minus, sorry. So, okay, let me do this. So, please cancel this, this is not delta g prime, right, this is just delta g, this is not the mutant, okay, this is not the mutant, this is the mutant, this is 6, okay. So, this is not the mutant, this is of the, what do you call that protein which is not a, which is found in the native state, wild type, right, I mean no mutation. So, this is for the wild type, so let me write it. So, this is for the wild type, this is for the wild type, and this is for the mutant. Okay, good. So, that means say a mutant is affecting a transition state in some way or the other, if you would be able to measure the kinetics and hence get the rate constant, you would be able to figure out the difference. Now, what difference are going to figure out? Okay. So, the difference is, this is what leads us to a very important feature which is used regularly in protein folding to try to look at effects in the transition state, what amino acid is affecting to what extent. So, what now I do is, I do 6 minus 5, I do 6 minus 5. If I do that, then I have natural log k f prime minus natural log k of f is equal to minus 1 by R t delta g prime u minus delta g u. Okay. So, then I can rearrange it and write it like this. I can write ln k f prime by k of f is equal to minus 1 by R t del g prime u minus delta g u. Finally, I will introduce this term delta g u is equal to R t natural log k f prime over k of f. Let us make this equation number 7. What is the significance of delta g? What is the significance of delta? We have encountered this before. the significance of delta delta G is it is the difference between two delta G's, right. And what are the two delta G's in this case? One delta G is coming from the wild type, the other delta G is coming from the mutant, right. So, you can think about two very extreme circumstances. One is that there is no effect, that means both these are equal, that is equal to 0. The other thing is, because we would be taking a fraction, the other would be 1, okay. That means both of these are equally affected in some way or the other. Now, let us see what we mean by that. So, the way we have written delta G out here is, I can rewrite it as, or the way the convention I did was this, is equal to delta G of the wild type minus delta G of the mutant. Now, this is the convention I put in. Okay. So, now see where I am going, this delta G u is essentially what? Is essentially G, that is the free energy of the transition state, right, minus the free energy of the unfolded state, is not it? That is what we know it by. Similarly, the delta G prime mu is the free energy of the transition state of the mutant minus the free energy of the unfolded state of the mutant, right. Okay. Now, if I label this say as equation 8, if I label this as equation 8, then using these two in equation 8, what we have is delta delta G u is equal to, what I can write is then G minus G u minus G prime of the transition state, this is the transition state, minus G u prime of the mutant. Okay. Now, can you tell me what this simplifies to? Let me give you a hint. Now, because you have this transition state and the unfolded state, why don't you group this one and this one, okay, and why don't you group this one and this one? So, what does this tell you? So, this is equal to delta G minus delta G u, isn't it? Isn't it, right? So, see, and this is something you know very well. That means, you just look at the you just look at the the energy pathway, the unfolded the transition state and all these things, and then you come up with this. Okay. Now, keep this in mind, because we would need this very soon. Now, let us look at a few diagrams of protein folding before we move on to the actual place where we use this equation we have just derived. Okay. So, let us consider some energy diagram. So, this energy diagram goes like this. So, there is a certain reaction coordinate on the x axis, on the y axis it is your free energy. Now, try to understand this figure. You look at the unfolded state, okay? You look at the unfolded state u. Now, in the unfolded state, you will see we have drawn many lines. What do those lines refer to? Ensemble of conformations, right? And you know in the unfolded state it is going to be maximum disordered, it will be having maximum flexibility. So, that means it would be having the maximum number of conformations available. So, you can see in terms of all the other states present, you have the maximum number of lines in the unfolded state. Okay. So, that is the starting point. Now, what you say is, okay, the next point is D, which is your denatured state, but under physiological conditions. Okay. So, this D phys means physiological. So, under physiological conditions, what might happen is that it might be having a little more compaction, it might not be as unfolded as it was, right. So, that is why see the number of lines has decreased. Okay. So, it has become compact. Now, from here you go to the transition state, that means you are going from the left unfolded state to the final native state. The transition state has only 3 lines. So, because the transition state after transition state going to move over to the native state, what will happen? The transition state would be having lesser number of conformation states, right, and then finally the native state is just one state, just one unique state. Okay. So, this is for the sake of argument, that is what we are going by. Now, if you go by this, there is no intermediate present, as written at the bottom of the slide. So, if I would write my k, okay, that means this is what, k folding or unfolding, what should I write? I am going from the left to the right. I should be writing k folding, right. So, that means I can write k folding is equal to, there was nu kappa e to the power minus delta g, and I can write a by r of t, isn't it? So, this is one case. Okay, we will be considering a series of cases. So, then if this is kf, that is what we are talking about, then I can write tau, which is tau f is equal to 1 by kf, and I say it is equal to tau a. Why? Tau a, because this is case a for me, okay, and tau f is essentially 1 by kf, that means the inverse of that, right. Okay. Then what is the next? What is another figure? Now, let us look at this. Here again there is no intermediate, but the small change is this. In the previous slide, the unfolded state and the denatured state under physiological conditions were the same energy, okay, only there was a compaction. But in this case what you are saying is that when it goes to the physiologically relevant state, still denatured, then there are some stabilizing interactions coming up. If there are stabilizing interactions coming up, what will happen? The free energy would be lowered, right, and hence this physiological here has a lower free energy than the u. Okay. So, your transition state is not affected, transition state remains the same. Then what will happen is you will be having a new barrier, which is delta g b in this case hash, and then you will go to n, right. So, here what I can write is k f is equal to again nu kappa e to the power minus delta g b by r t. Okay. But what is delta g b equal to for me here? Can I write this? So, delta g b, where should I write? Let us see if I can squeeze it here. Delta g b is equal to delta g a, which was there before in the previous one. Now, tell me what should I write? Plus, can I write this g u minus g Can I write this or not? See, this is by how much? It is stabilized. And what is this? This is essentially g u minus g of d physiological, right. So, then what has happened to the barrier? The barrier has become larger. So, if the barrier becomes larger and this is tau b is equal to 1 by k f in this case, then I can write here tau b would be greater or lesser than tau a. Tau, it is the folding time, would it be greater or lesser than tau a? It is greater than tau a, right. So, that means tau a, so the case a you would be folding faster than b. Why? Because your energy barrier is increased. Why? Because your physiologically denatured state, which you are considering, is stabilized as compared to the unfolded state, and has come down in terms of the free energy. Clear or not? Is it clear? Okay. So, this is very similar to what probably you guys have done in terms of have you done Hammond's postulate and all these things in physical organic chemistry by any chance? Okay. Now, let us consider this. Here we are now invoking an intermediate, the presence of an intermediate. Now, what does the presence of intermediate do for you? In this case, it just gives rise to another state, an intermediate, which is I here. So, this is the intermediate, but here this intermediate is high energy intermediate. So, the intermediate essentially does not what affect your kinetics, So, in this case your Kf is still what? It is still delta Ga, that hash sign. So, here Kf is equal to nu kappa minus delta Ga by RT, where tau f is equal to 1 by Kf, this is say tau c, and then I can write tau c would be equal to tau A, because it is the same thing. So, if tau c is equal to tau A, that means both of these are of lower value than tau b. Okay. Now, can you tell me what is the last? So, there would be another alternative to this. What would that be? So, the intermediate has come down lower, right? Okay. So, then so this is what exactly happens now. You can see the intermediate has lowered down. Now, if the intermediate is lowered down, this process has two steps. What are the two steps? High energy intermediate did not matter to your kinetics, but the low energy intermediate would matter. Why? Because you would be having two phases. What are the two phases? This one would come here. So, that is K1, and this one would go all the way from here to the native state, and that would be say K2. Okay. So, which one is more defining in terms of your rate? K2, because that is a much bigger barrier. So, in this case, what is delta G d equal to? What is this equal to? Tell me now. You start with this, then what should I write? See, when it was, remember the second case, no intermediate, it was G of u minus G d. So, in this case u and d are the same essentially, but I am talking about this d and I now. So, I can write plus G d physiological, then what is the next one? Minus G of I, isn't it? So, that means this delta G d double dagger is essentially, or hash is essentially from the intermediate to the transition state. It is no longer from D, because this intermediate is not high energy, this is a low energy intermediate. Now, you can immediately realize what will happen to tau d. Tau d would definitely be less than tau A, rather more than tau A and tau C. So, that means I can write tau d. So, if this is d, then tau d would be greater than tau A, and tau A was equal to tau C. The simple reason being your intermediate has stabilized now, and hence again your energy barrier has gone up. Okay. So, these are 4 very simplified instances, but covers the most of protein folding in terms of the basic premise. The first two were no intermediates, the second two you started considering intermediates, right. Now, this is just one intermediate, you might be having a series of intermediates, then accordingly that will vary. Okay. But what is the take home point from here? How do we look at this? The rate of folding drops when D physiological is at lower energy than that of U, that we saw. Okay. Good. Now, any intermediate between the D physiological and transition state that is of lower energy than that of D physiological will slow down the rate of folding, that is what we just saw. Okay. High energy intermediates do not essentially slow down, right, because they are not affecting your kinetics. So, for our case we do not even bother about the high energy intermediates. Good. Now, what are the consequences? Now, think about this. The consequences, if you would be having intermediates and if those intermediates would be of low energy, what would happen? Your folding rate would be affected and that would be lowered as compared to that case where you do not have any intermediates. So, this is what we mean by a fast folder. Essentially, chymotrypsin inhibitor 2 was a fast folder. Why? Because it did not have an intermediate. It was what? It was lacking intermediates. Hence, it could fold faster than say another chymotrypsin inhibitor 2 hypothetically, which would be having an intermediate. right. That is what it is trying to say. Okay. Now, stable elements of structure in the physiologically denatured state slow down the rate of folding, since they lower down the energy levels of dephase. That is what we have also seen. This is just being rephrased. There is non-native interactions such as extensive hydrophobic interactions in the physiologically denatured state would do what? Would affect your folding rate by slowing it down, as compared to the case where you would not be having any such stabilizing interactions present. See, here I am not talking about intermediates, I am only talking about what? The cases A and B, where there was no intermediate, I only had the dephase. In case A, the dephase was almost the same as U, or was the same as U, and the second case, which is case B, dephysiological was of lower energy than U. Good. So, formation of stable elements of native structures in the dephysiological is also unfavorable. Now, see, how do you rationalize this? Okay. How do you rationalize this? So, let us just look at this real quick. Okay. Now, suppose I am considering this chymotrypsin inhibitor too. Okay. And remember, if you remember the structure of the chymotrypsin inhibitor 2, I had a helix there along with the other beta strands. Now, suppose you do something. What you do is you put in certain amino acids, like say you are redesigning the protein, you are putting in some certain amino acids which stabilizes the helix. In what sense? What it does is, if it is stabilizing the helix, it is stabilizing the native state, because it is stabilizing the helix, and it is also stabilizing the transition state. So, this is what I mean. Now, I will draw it very simply. So, this is your unfolded state, okay. This is your transition state, and this is your native state. Okay. Right. Now, I have gotten rid of all those different lines, right, very simple. Now, what is happening is, you are putting in helix stabilizing amino acids. If you are putting in helix stabilizing amino acids, what will happen? Now, I am saying is, in the first case, the transition state is affected, so is the native state. So, the native state is being stabilized, but the unfolded state is left unaffected. Remember, the unfolded state is left unaffected. Okay. So, if the transition state comes here and the native state comes here, say, okay. So, this is say T s prime and this is n prime. Okay. Now, tell me, under this new modification which you have introduced, what happens to the folding rate or what happens to the folding time? Is it lesser? Is it folding faster or is it folding slower? It is folding faster. You can understand, it is folding faster, because the barrier, effective barrier has decreased. Why? Your unfolded state was not affected. Okay. So, that means this barrier is lower than this barrier, that means this one is greater than this, right. So, this barrier is greater than that barrier, and hence in this case what is happening is, your tau prime is less than tau, where prime is belonging to the mutant. Good, no problem. Now, think about the other consequence. The other consequence is, now until this point we had said the unfolded state was not getting affected, right. Now, you put here, now you are putting in helix stabilizing agents to such an extent that it is also affecting the unfolded state and is also stabilizing the unfolded state. So, do you understand now what is happening? Initially, when you did it, you introduced the mutations in such a way, or introduced the amino acids in such a way that it was only affecting the native state and it was affecting the transition state. Okay, this is just an assumption, please, okay, let us just go by it, right. Because you get the native state from the transition state, then transition state follows the native state essentially, or native state follows the transition state, it follows the energetic consequence, and hence both of them are stabilized. But the unfolded state stays where it is, and because the unfolded state stays where it is, its barrier gets decreased. Now, the moment you make some other mutations which also stabilize your unfolded state, what happens? If now you stabilize the unfolded state, this will also come down. So, this is U double prime, which is the second mutant. Second mutant is, that means you are also stabilizing unfolded. Okay. Now tell me qualitatively what would happen to tau? Would it change or would it not change? Do not worry about the absolute value, just tell me. It would not change, right? It would not change. Why? Because you see, not only have you stabilized the transition state, you have also stabilized your u, and hence the energy barrier has effectively what remains the same, isn't it? Okay. So that means in this case for, so I can say that tau prime would almost be equal to tau, and tau double prime would almost be equal to tau. It's clear or not? Good. Why did we go to this discussion? And try to understand this. In the previous slide, we had, in the previous slide, let us go to the previous slide. Look at the last sentence. What we said is, formation of stable elements of native structures in the physiological denatured state is also unfavorable. Now, why did I say that? See, if you are stabilizing something, we should not be saying it is unfavorable, right? We should always go towards that. But the problem is, when you stabilize the unfolded state, you are not doing anything. Are you doing anything? Because you just saw, when you stabilize the unfolded state, because that is where you are going, if it is just the mutant which is not affecting the unfolded state, no problem. But if your mutant is stabilizing the unfolded state, there is no change in the free energy barrier. If there is no change in the free energy barrier, the protein does not change anything. It is taking the same time to go to the to go over the barrier. So, think about it logically. Why would evolution go for that? Because you are putting in more energy stabilization at the cost of what? Nothing. So, you would not do that, isn't it? This is the crux of the matter. I would not try to randomly stabilize my protein, because finally it is of no consequence to me. But listen, when I am doing this energy stabilization, I am actually doing some modification. I am using these extra stabilizing interactions, but finally I went in with these extra stabilizing interactions and I came out with nothing. It was of no consequence to me in terms of the protein folding scenario, that means the protein folding rate. Do you get the point? So, you would just not do any random mutations, right? Or in other words, you would just not try to stabilize it as much as possible, because these things can happen, and finally you would not get anything out of it. Okay. So, then to rephrase it, there is the window of stability. Remember, we are talking about these local structural elements. If you remember, we started from the nucleation condensation mechanism, where in nucleation condensation we had said that to form the nucleus you would be having adjacent local elements which would come and stabilize and form the nucleus. Okay, this we are talking about the local structural elements. So, it says that there is a window of stability for a local structural element. Now, what do I mean by that? The window is like this. If too weak, it will destabilize the folded state. I would not want that also. So, you are trying to maintain a balance. See, if the local interactions are too weak, then even in my folded state it would be weak, no matter how my tertiary interactions are, and hence it would not be that stable. So, that is not called for, that is not something you would want to do. Okay. Also, if too stable, what will happen? It will overstabilize the unfolded state, then also it is of no consequence to me. One is you understabilize, that means you destabilize the folded state, that is the problem. Okay. The next is you do not try to overcompensate by overstabilizing, then what you are doing? You are stabilizing the unfolded state, then again you are having no change. Okay. You are wasting your good stuff. So, then what is the window? The window is always between these two, isn't it? And this is your window of stability for your local structural elements. You will not go one way or the other, you would always try to remain within these 2 points, keeping this energetic consequences in mind. Is it clear? So, this is what is extremely important. If you would try to design a protein, if you would try to mutate a protein or engineer something, you would have to make sure that these things are not happening. One is, obviously you are not going to destabilize the protein, because the folded state will destabilize and the whole thing falls apart. It is very unstable for you to see. And the other one is, you do these mutations, but finally when you do the kinetics you do not see anything. Why? Because you have also tweaked the unfolded state, because you are over careful. Being careful is good, being over careful is bad, right? That is the point. And it is like this, I will tell you a very, maybe it just happens to me. See, in my office there are many papers, right, many different papers I lose track of, but if you ask me to find one, probably I will find it. Okay. You give me say 5 or 10 minutes or maybe a little more than that. Now, suppose I get the paper and I put it somewhere else and I forget where I have put it. I was being extra cautious now. So, what has happened? No matter how much time you give, if I do not recall where I have put it, I will never be able to find it. But I was being overcompensatory. I was being overcompensatory for the fact that I have so much stuff on my table, I would put it in some other place where it would be safe and secure. It was really safe and secure because I forgot about it. Okay. This is exactly what you are seeing out here, isn't it? I mean, it is very simple, at least from my standard to understand, because I am doing it every day. Okay. So, yeah, I will just let me finish this part. I will start with the next one, next class. So, thus it is favorable for a nucleation site to have a group of adjacent residues that is a part of an helix, not stable by itself, but becomes stable by interacting with other residues elsewhere in the protein. Okay. So, that it is not stable by itself, right. And this is your classic nucleation condensation mechanism. Now, hopefully, you will understand where this nucleation and condensation term comes in. This is where it comes from. You would not stabilize it too much, you would also not destabilize it too much, that it would never form the nucleus, because if you destabilize it, the local elements interactions would be low, it would never form the nucleus, your protein would never go, or even if it does go, it will be having a very low stability. Okay. Right. So, the next class we will start with something known as 5 value analysis. 5 value means how do you actually probe the transition state, that means how do you actually probe to what extent a mutant is changing your energetics. Okay. That is what we would probe next class. Okay.